Welcome, everybody. My name is Brad Keeler. I'm the director of the Geo-Institute of ASCE, and we are very happy to welcome you to our first live stream of 2022. You have not entered some other dimension. I am coming to you from an airport in the Southeast United States. Our speakers are in much more comfortable digs where they will be comfortable presenting to you. If you do not know anything about the Geo-Institute, we are a technical society. We have about 12,000 members, most of whom are geotechnical engineers and or geologists. We are part, as I said, of the American Society of Civil Engineers. Today, we come to you with our first pre-conference workshop for an event we're holding later this year, the International Symposium on Frontiers and Offshore Geotechnics. ISFOG. It'll be in Austin, Texas at the end of August, and we hope you are there with us. If you like what you see today, please click subscribe. Please click get notifications. We will let you know every single time that we post a video to our YouTube channel, which is really frequently. After this presentation is done today, that is where this will reside until the end of time or until YouTube shuts down, which we hope does not happen. So today our presentation will be on data management. It'll be with Bruno Stuyts of the University of Ghent in the Netherlands. And here to tell you a little more about it before we get started is one of the members of our program committee, Rodolfo Sancio of GeoSyntech. Rodolfo, take it away.
Well, thank you very much, Brad. I believe I'm sharing my screen and that's live. Well, welcome to the 4th International Symposium on Frontiers in Offshore Geotechnics, ISFOG 2020 in 2022. This is the first pre-conference webinar series, and we're really excited about today's presentation on Data Science 101 by Bruno Stuyts. I know this morning we had over 600 registered participants from throughout the world, and I hope that most were able to join us today. Before we move on to the webinar, I want to provide some key information about the conference. So please write down these dates. On Sunday, August 28th, we will have 6 one-hour-long workshops. From Monday to Wednesday, we'll have plenary and parallel sessions that include 6 keynote lectures and the McClellan Lecture. The proceedings have been available for purchase since August 2020, and they include over 200 technical papers. Early bird registration starts March 9th, 2022 at isfog2020.org. As mentioned, this is the first of 6 pre-conference free webinars. As you can see, the cast of presenters is loaded with top-notch academicians, researchers, and practitioners in offshore geotechnics. Please join us for this one and the 5 that remain. I'm sure that you'll be able to learn quite a lot about offshore geotechnics and get pumped up and ready for ISFOG 2020 later this year. I want to take advantage and recognize and thank our conference sponsors. We have platinum sponsors, gold sponsors, silver sponsors, bronze sponsors, and we have also, if you visit our website, a long list of exhibitors. We are always welcoming more sponsors and exhibitors, and as well as sponsors of the remaining 5 webinars. If you're interested, please reach out to Barbara Curtis. Her email is right there, bcurtis@asce.org. Moving on, I want to introduce today's speaker. Bruno Stuyts is currently a visiting professor at Ghent University in Belgium. He earned an MSc and Master's of Science degree in Geotechnical and Mining Engineering from KU Leuven in 2006. From 2006 to 2018, he worked in offshore geotechnical consultancy. Over the course of his practice, he has been involved in offshore oil and gas and renewable energy projects worldwide, including several joint industry research projects to improve geotechnical design practices. He has a strong interest in multidisciplinary approaches for the design of offshore structures. In 2019, he was appointed as visiting professor for offshore geotechnics at the Geotechnical Laboratory of University of Ghent. He's responsible for the Offshore Foundations course and supports the other geotechnical courses in the curriculum. His research interests include monopile soil structure interaction, the influence of geotechnical properties of backfill on cable soil interaction, and the application of data-driven methods to geotechnical design. He is currently developing the laboratory infrastructure required for cyclic testing of soil and 1G model testing of soil structure interaction. In parallel to his position at University of Ghent, he is currently pursuing his PhD on the use of in-situ monitoring data for lateral response predictions for monopiles at OWI Lab, a partnership between University of Ghent, University of Brussels, and the Belgian offshore wind industry. And now, without much more, I'll leave you with Bruno Stuyts.
Thanks, Rodolfo, for that introduction. So let me kick off by sharing my screen. I hope that everybody can see the slides, and then we're good to go. So I'm very excited to kick off this webinar series with a talk on data science. In this talk, I'll be giving you some insights in why data-driven methods matter for us, and especially for us as offshore geotechnical engineers. One of the main challenges that we have in AI is to make it accessible for people. So I'll talk a little bit about how to get started with AI and how you might already be a bit further than you think with applying these methods and knowing what they're all about. Data is really central to anything involving data science, so I'll talk a little bit about my views on how data should best be harvested, processed, and presented in order to communicate effectively, not only with geotechnical engineers, but also with people who are generally having an interest in the project and the conclusions that can be drawn from the data. Then I'll dive in a little bit deeper to show you some details on a couple of common machine learning workflows, looking at classification and regression problems. And when we talk about machine learning, we have to talk about the performance of models. And so performance metrics and knowing how to interpret machine learning results will be central to actually making sure that our data science products work to make good decisions. Everything that I'm talking about today is based on the ISFOG 2020 data science keynote, which is already available in the proceedings. So if you haven't got a copy of the proceedings yet, make sure to either buy them or register for the conference, which includes access to those proceedings. People often ask me, how should I get into data science, and what is the best way to learn about data science? So I find that a difficult question to answer, but I wanted to provide a bit of insight into my own journey into this interesting field. And as Rodolfo mentioned, I've started in offshore geotech since 2006. But I think one of the defining points in my career was the introduction to Python scripting. That was through the Abacus scripting language, because the Abacus 3D finite element program can be scripted using Python. And that really opened up a door towards automation and basically more structuring in terms of code and how you build workflows. Combining that with my interests, which were on the probabilistic side, so working with statistical data, on numerical methods and automation, I think I found a really good match, something that I was very excited about, and I wanted to learn more. I also found that during my work, that there was often a lot of data being lost. And that was not really through any bad intentions, but the fact that in offshore geotech, we're mostly working on a project basis with data stored in project folders. And then once the projects get closed, the data is still there, but you sort of never look back into the folder. That can be a source of data loss, something that we want to prevent. Because if we go to a site and we already have info from an adjacent site, that should put us in a better position. Also, I developed a very difficult relation with Excel, because Excel, although it's commonly used and it does good things, has a couple of drawbacks that I saw mostly cured by going to structured code and Python. Even though people can be very skilled at building Excel sheets, I sometimes found that version issues were arising. People were using old versions of the spreadsheet, whereas a newer one should have been used. And also there is sometimes a lack of transparency with formulae being filled into cells or being hidden in VBA macros. So bringing that transparency to offshore geotechnical workflows is something which I found very easy with Python. So I made a conscious switch for myself to switch from Excel-based workflows to managed code with Python. Last year, I then decided to publish some of that geotechnical functionality as open source. So Groundhog is a package which includes functionality, for instance, for CPT processing, and can simply be accessed and downloaded online. I also use scripting a lot in my research and in my lecturing. And for students, I found that using scripts allows them to process geotechnical data quicker, with more insight, and it builds up their basis of experience a bit quicker. But I do not deny that there's a learning curve attached to scripting. You can see that I've been doing it since 2008. So don't expect any miracle solutions, but in the rest of the talk today, I hope that I'll get you excited about also using scripting, or at least getting into data-driven methods with the tool of your choice. When we are working on offshore geotechnical projects, data collection is really central to what we're doing. Without data, we would essentially be blind, and we have to recognize that doing site investigation offshore is more costly than doing it onshore. And as an individual project, there's often only limited resources to go out and collect data. Usually for feed design, we have a fairly limited survey, followed by a more detailed survey once the project gets the go-ahead. In Europe, it's sort of the norm to have a single CPT test at every foundation location, supplemented with selected borehole locations. But even that, we can ask whether that is sufficient. Because if you're working on a site with a lot of lateral variability, even one CPT test per foundation location may not be sufficient if you're putting a jackup down with 4 legs, for instance. In TC 209, we're trying to address this issue, and that's really work in progress. But what we are trying to assess is what we can do with the amount of data that we have available, recognizing the limit in the amount of data, especially when the testing gets more expensive, like in-situ seismic CPT testing, ring shear testing for axial pile soil interaction, or cyclic testing to assess the cyclic stability of foundations. This graph from a previous ISFOG keynote by Trevor Evans in 2010 showed the optimum spend for deep water site investigation, and it showed that an optimum spend of between about 1 to 2% of CapEx was sufficient site characterization. If you characterized less, you would pay the price in terms of consequences and unforeseen soil conditions. If you paid more, you would basically gather redundant data. That graph applied well to deep water sites for which it was developed, but for offshore sites, and especially now that we're developing wind farms, we have to maximize the value from already available data. And in addition to spending money on site investigation for the specific project site, collecting geological information, geophysical data, and previously recorded tests in similar soils can help us out a lot. And in offshore wind farms, we typically see 3D ground modeling being the norm rather than the exception. What we also see is that the CPT is very popular for offshore wind farms, and CPT-based correlations are commonly applied to soil parameter estimates. But we can ask a question there which is very relevant, because every correlation was developed based on an underlying data set. So we take previous knowledge into account, but we need to assess whether that knowledge is actually fit for purpose, whether the same soil types are used, and whether the same stress conditions, for instance, apply. Also, correlations inevitably have a scatter, and if you don't take that into account, you might have too much confidence in your estimates. So the question there, which is relevant for data science, is what if we could establish site-specific soil parameter correlations? So for the specific soils that we have at our site, based on the data sources which we believe are relevant, and then use AI to build predictive models. The second thing, which is really now accelerating AI in our profession, is a quantitative integration of geophysical and geotechnical data. So geotechnical data is collected at specific spots in the wind farm site, and in between those boreholes, we essentially have no real in-situ test data. But geophysics can fill in the blanks between those point measurements, and we can invert geophysical data, so back calculate the elastic properties of the subsoil using high-resolution geophysical data. And once we have those elastic properties, we can compare the elastic properties at known borehole locations to other geotechnical parameters, such as cone resistance, such as friction angle, to come up with a quantitative ground model in which we can assess the values of geotechnical parameters at locations which we haven't yet investigated. And AI and machine learning allows us to make those correlations and also establish an uncertainty band on our estimates. The final thing, which is really exciting for AI, is that in addition to site investigation, we're doing other soil testing, which we might not even see as soil testing. Because when we do foundation installation, we are essentially probing the subsoil yet again and confirming our assumptions from design. And our current design practices and installation calcs are based on semi-empirical methods from codes and standards. But what if we used the in-situ field performance instead and calibrated either those methods or new methods for which we find new features to the data that we observe in the field? Because the data on which codes and standards are based essentially do the same thing. And often they're based on a fairly limited data set. And like we've seen for offshore wind turbine monopiles, there are sometimes issues with scale, because the API method, method for lateral pile response that was developed for smaller diameter piles, had some shortcomings when extrapolating that to larger pile diameters. So foundation installation data can be used to train AI models, and I'll show a little bit how that works for pile driving. But jackup, leg penetration records, suction caisson under pressure records, those could all equally be used to calibrate new foundation models which are purely data-driven. I already mentioned that getting started with AI is not necessarily that easy. You need to find your own path forward, but it does help to look at the basic definitions of artificial intelligence and machine learning. So Google has a machine learning glossary, and if you look at the definition of artificial intelligence, you'll find that it's fairly mundane. It's actually just a non-human program that can solve sophisticated tasks. And machine learning is then a subfield of AI in which we train a program with input data to predict the outcome on new samples. But if we compare that to our current geotechnical engineering practice, we see that actually a complex computer program that we build to solve problems is nothing different than the stuff that we're using in routine engineering. So if you build a 3D numerical model or even a spreadsheet, you could consider that under the definition to be a form of artificial intelligence. Machine learning has also been performed by many of you because, as I mentioned, we have all of those CPT-based correlations or other soil parameter correlations based on laboratory testing. And we try to find the best fit line that fits our data and approximates it as well as possible. And under the definition of machine learning, that is exactly what it is. We try to calibrate a mathematical model with input data to then make future predictions. So you may ask yourself, what's new? And it's actually more the techniques and the tools to handle AI which are new today. So in recent years, we've seen increasing availability of machine learning algorithms. And if you consult a package like scikit-learn, you will find that it puts many machine learning models, including very complex ones, right at the fingertips of engineers. The mathematical complexity is largely hidden, and you can simply build a model using just a few scripted statements. Also, the amount of data that is available digitally that you don't have to digitize yourself from a PDF is increasing. There have been good drives forward in terms of the AGS and DIGS standard to make data digitally available, and having that is really the lifeblood of AI. Also, recording construction feedback digitally and monitoring data through Internet of Things, for instance, can provide us with more data to work on to perform AI. The computational power of our individual laptops is often sufficient for many machine learning tasks, but if we do need to scale up, the cloud is there to help, and we can actually rapidly scale up machine learning workflows by using the computation capacity in the cloud. But still, if you look at the cartoon here, AI relies on the people that are using it and are putting it to good use. So you can ask yourself, should I learn scripting? Well, I think a good case can be made for scripting, but you don't necessarily have to. Even though scripting allows you to automate and to vectorize workflows. So imagine in Excel that you drag a cell down all the way, and then depending on how long your CPT trace is, you have to drag it further or not. Well, in scripting, you can do all that in just a single statement of code. And that obviously helps, but you can also gear an organization towards more data-driven working if you tune all the tools together so that people who work with Excel can feed knowledge to the people which are programming tools. Also, we are seeing that there is a drive forward in no-code machine learning platforms. So basically drag and drop programs that allow you to build machine learning models from CSV data, from databases or whatever, without needing detailed scripting knowledge. If you do decide to learn Python, there's many high-quality resources available online today, some for a small cost, others for free. And also for geotechnical exercises, there is a number of public community exercises available, including the ISFOG one, which I'll continue on a bit later. When we're working with data, we have to, first of all, ask ourselves some questions when we get a data set. And those questions are very relevant because, first of all, if we're looking at a certain problem, we have to ask whether we're collecting the right kind of data. If we're looking at cable-soil interaction, a deep borehole might not be the solution. We can also ask ourselves whether we're collecting sufficient data. Are we capturing the variability in a site through the amount of site investigation that we're specifying? And also, any measurement has a measurement uncertainty, and especially for laboratory measurements, we need to make sure that the people who are performing those measurements are doing it according to the highest quality standards so as to minimize effects of individual sample preparation or lack of quality in the execution of laboratory tests. Data storage plays a big role as well, because what we find with data in general, with geotechnical data perhaps less so, but in any case, file-based storage has its limits. Files can get lost. Files may get very large if you're collecting a lot of data. And we need to take into account what's going to happen to all of that site investigation data once the project is over. And that's where cloud-based geotechnical data management can offer solutions. And I would just like to draw a small parallel to other sectors and how they handle their data. And then I would like to make the parallel with the flight booking platform and the flight pricing information that they get from their airlines. Imagine that you want to book a flight to the ISFOG conference in Austin, which I all hope you'll do. Then you will select your destination. You will say that you want to be there from the 28th to the end of August. And then the search engine will return a list of all available flights to Austin. Based on your travel needs, you will select the flight that is best suited for your schedule, and then you will select a fare from the list of fares which is returned and proceed to booking the flight. There is no doubt in your mind when you do that, that on the date when you've booked the flight, there will be an airplane ready there to carry you to Austin to enjoy the conference. What if we could have the same confidence in geotechnical data collection? So if we have a certain project and we want to design a foundation, we say where our foundation is and we get a list of available boreholes. We then select the borehole or boreholes closest to the foundation location, getting a list of samples, and then get, for instance, direct simple shear test data in a depth range of interest for the soil unit that we're looking at to proceed to calculations. If we can have the same confidence in the data that comes out of such a workflow, we could make our lives as geotechnical engineers much easier. And then once we get the data, there will be a data processing task. And as you've seen in the previous slide, data processing is actually what data scientists spend most of their time on. We want to check the data for consistency and quality, and check whether any outliers are actually representative for actual foundation behavior. We could decide to partition our data set, only look at sands, only look at clays. That can lead to improved accuracy, but it has the downside that it will also shrink the size of our data set. When we are looking at data, the raw data only paints part of the picture, and we can use either engineering knowledge or knowledge from nearby boreholes to enhance the data, to, for instance, calculate vertical effective stresses, or to supplement seismic CPT measurements with conventional CPT data, to make correlations, for example, like shown in this picture, between cone tip resistance and small strain shear modulus. In that respect, we can also mention feature engineering, because feature engineering is the process of enhancing the features in our raw data, the measurements that we have, with features, measurements, or calculated values which carry more information. And for CPTs, we all know the CPT-based parameter normalization, the normalized cone resistance, leaf friction, and BQ parameter, soil behavior type indices, for instance, and all of that uses some kind of underlying knowledge of the physics, for instance, the stress dependence of the soil. And with that knowledge, we can enhance the value of our data. For some problems, integrating something over depth also helps. If we look at profiles and, for instance, look at axial capacity, we have to integrate unit skin friction over depth to get an estimate of how much power resistance we'll have at any given depth. So a depth integration could enhance our knowledge. We also have to recognize that some data is operator dependent. For instance, while you're pile driving, if your operator is targeting a steady blow count, just wants to advance at a given number of blows per meter, then that blow count is not going to carry a lot of information, is not going to differentiate very well with in terms of soil behavior. You could then choose to transform that output to a more meaningful variable, for instance, looking at the amount of energy needed to advance a certain increment of penetration. The data that we should be targeting should allow us to differentiate between different ground conditions and different operational conditions. And so having those features available in a data set will help a lot in the machine learning task. Data presentation is really essential before we start any machine learning, because presenting the data will give us insight in the data and reveal trends and possible clusters in our data. One very useful tool is the scatter matrix, and a scatter matrix is a matrix of plots which has a row and a column for each soil property. And on the diagonal terms of the scatter matrix, you have a histogram of the properties, and on the off-diagonal plots, you will put plot one parameter against the other. This will reveal the statistics of the individual features in your data set on the diagonals. And then on the off diagonals, you will see potential correlations in your data. And here for a CPT, for all CPT data that we see, we can observe that there's not that much correlation in our data set. And we might have to dig a bit further to visualize that data better. We could do that through violin plots, and violin plots are basically an enhanced box plot. So if you know the box plot from descriptive statistics, it includes the mean, the 25%, 75% quantile, and then mins and maxes. And the violin plot plots the distribution of the data on top of that box plot. It can show you where the data is most concentrated and which values are really very much in the tail of the distribution. All of that visualization and that exploration of the dataset will guide machine learning modeling. And machine learning modeling is really an iterative process in which you really get to know your data intimately and discover new knowledge once you're doing it. So let me dive a bit deeper into some common machine learning workflows. And if we look at classical machine learning, we can make a distinction between supervised and unsupervised learning problems. In supervised learning problems, we will try to make a prediction based on input data. And we can make a distinction there between classification, where we're trying to predict a certain class, for instance, the soil type from CPT info, and regression problems in which we predict a continuous variable, such as pile driving performance from soil pile and hammer data. In unsupervised learning, we're trying to get more insight in our data in terms of clustering, for instance, establishing areas with equal susceptibility to settlement or to liquefaction, reducing dimensions, so trying to find the most influential features in a certain data set, the features which have the most influence on an output parameter, or associating certain features with one another. In this talk, I'll be talking about supervised learning because that is what we'll do in geotechnics most of all to formulate predictive models. In the examples, I'll use two data sets. The first data set is a classification data set where we took 16 boreholes with combined CPT and sampling from the Borselo 1 and 2 offshore wind farm areas in the Netherlands. That data is publicly available, made available by RVO under a Creative Commons license. And as well as sample descriptions, we have downhole CPT data available to 80 meters depth. Combining that CPT data with sample descriptions allows us to formulate predictive models from CPT data, and I'll show you in a bit more detail how that is done. For regression, we have a pile driving data set, which was part of our ISFOG 2020 data science competition. And the data was collected for the installation of 114 jacket piles in the North Sea, mostly in sand. And we had a CPT at every foundation location, pile dimensions and blow counts and hammer energies recorded during installation. The aim there was to predict the blow count from the available soil and installation data using only that data to train a model. You can ask yourself, when you're approaching a certain problem, whether you should approach it as a classification or a regression problem. And the answer to that is, well, that it depends. You can use the same data to formulate both a classification and a regression problem. If I take that in terms of the pile driving problem, if we look at regression, we would try to predict a continuous blow count based on the CPT and hammer data. But if we would use that as a classification problem, that would be equally possible. But then instead of predicting a continuous variable, the blow count, we would try to predict a blow count class, so between 0 and 25 blows, and so on in classes of 25 blows or whichever classes you choose. Which type of modeling you want really depends on the expectations that you have from the modeling. And if you want to have something which gives you a go, no-go outcome, then I think perhaps a classification problem might be a better solution. If you want something which predicts a continuous variable, then you need to look at regression. In general terms, if we do look at some basic definitions and a way to call things in machine learning, we can say that there is a relation, or we think that a relation exists, a true relation between features, so known values such as cone resistance, such as hammer energy, and a target, so an output, a blow count that we can measure. That true relation will remain unknown to us, especially in geotechnical problems where you have scatter. But we can try to approximate the relation using a model, an imperfect representation of that relation between features and target. And then rather than giving the exact blow count, the model will predict a blow count which should approximate the measured value as closely as possible. And any machine learning model, so any model that tries to predict behavior, will try to minimize that difference between the prediction and the actually measured value, which we call the loss. And a loss function such as root mean squared error is then minimized to tune the coefficients of the model. If we take that in terms of our regression problem, then we can say that the blow count is our target variable, and then we will build a model using input features such as hammer energy, cone tip resistance, vertical effective stress, pile wall thickness, etc. It really depends what we think are useful features that will have an impact on the outcome. Building machine learning models is all about selecting that type of model and then tuning it to the input data. And if we look at the difference with traditional programming, in traditional programming, we already know the rules that we're going to implement. We write down the equations and we put them in a computer to then give us a result when we present new data to the computer programming. In machine learning, we don't know the rules to start with, but we will take a general form of mathematical model and calibrate it to fit our sample data as well as possible. Those rules are then available in some kind of computer representation, and that model can then be used to make predictions on new data which has not yet been used to train the model to give us a result. When we're trying to fit a model and are making choices for our modeling, we should acknowledge that some problems are more complex than others. And if we select a model, we should select one that captures the complexity of the relations between the features and the target. If we have a model which is not sufficiently complex, such as the linear model shown there for the data set that we have, then that model will underfit the data and will be insufficiently capable to capture the complexity of the observed trends. If we do take all of the data into account and try to fit each individual data point, then you have a model which is very erratic and that's also not really what we want, because our model is influenced too much by the exact values of the measurements, which inevitably also have some kind of scatter. And we call that overfitting, where the model is too complex and does not perform well on unseen data. So, as well as having good accuracy for the model, we also need to check whether our model performs well on unseen data, and we call that model generalization. For model accuracy, we have a number of metrics in machine learning, but you may already know those metrics from other courses or classes that you've taken. And things like a mean absolute error, a mean squared error should be fairly straightforward, because we compare the predicted and the measured value of our features, the predicted and measured values of our target, and calculate the mean over our data set. The R squared, or coefficient of determination, is an interesting one, because R squared explains to us how well the model is capable of representing the variance in our data set. And if we have a model that is perfectly capable of capturing the variance in the data set, then we have an R squared of 1. So we're trying to target that R squared score when performing our model. It's usually good practice to take a couple of metrics to establish the accuracy of a model. In terms of classification accuracy, you could formulate numerical metrics such as the accuracy score, so the total amount of correctly predicted classes over the total number of predictions to get your accuracy. But sometimes a graphical representation of model performance can also be instructive. And that's where the confusion matrix comes in. Actually, contrary to its name, a confusion matrix is anything but confusing. It really gives a very nice graphical presentation of model performance, because on the rows, we will get the true classes of the target, and on the columns, the predicted classes of the target. And if we apply that to an example problem such as COVID-19 self-testing, we can see that if we have a positive person, so somebody truly has COVID and they test positive, then that's a good thing. That's a true positive. We've detected illness where we had to. The same applies for true negatives. If the person is not sick and takes a negative test, that is the desired outcome that we want. Things get messy when we don't have true positives or true negatives, because if you have a false positive, you might be quarantined and then it really is to no effect because you're not sick. If you have a false negative, then that is not good either, because you will infect the population some more, and that is obviously not what we want either. So that principle works equally well when we're trying to predict multiple classes, and the confusion matrix gives a very quick and graphical representation of the machine learning quality. Remember that we had to test the performance of machine learning models on unseen data. That's where generalization techniques come in. And for that purpose, when we have a given data set, we will always split it into a training set, a validation set, and a test set. During the training of the machine learning model, so the calibration of the coefficients of the model, we will evaluate the performance of that trained model on the validation set and check whether comparable accuracy is obtained on the validation set and the training set. And the test set is then a test that we hold out for final acceptance testing of the machine learning model. You may wonder if partitioning the dataset itself doesn't introduce any bias, because you may select only data points which have clay in the training set and then have some sand points in the test set. Well, in order to avoid that, it's a good thing to perform that splitting a number of times, and we call that k-fold cross-validation. In k-fold cross-validation, we will calculate the accuracy for each partition and then compare the average, and ideally all accuracy scores for all splits should be comparable, and there shouldn't be too big a difference between the individual partitions. In geotechnical applications, we have to recognize that soil conditions always play a role in the partitioning. So if you have a data set, it's good to mix soil types between each other if you're really trying to predict the behavior over all different soil types. If you're really trying to predict for only one particular soil type, it's better to train and do the entire model on just the clay data, for example, if you're targeting only clay. In geotech, we're also working with depth-dependent problems a lot. So location-based partitioning might make sense. So holding out entire locations to then predict the profile of axial capacity of blowcount, for instance, that might be meaningful. So now all there is to do is to look at a couple of selected machine learning models. This one is really the one that I like to start with, because linear regression is known to everybody, and it's one of the easiest and most interpretable machine learning models. In linear regression, we will calibrate the coefficients A0 to AN to give a best fit to our data. But this implies that a linear relation does exist between the features and the target, and that is not always the case. But we can coerce problems into a linear format by linearizing the relations between features and target, and also making sure that those relations are transformed to a linear feature space. The advantage of linear models is that the trained models have a mathematical form, so you can simply share a calibrated equation with any people that you're communicating with. And on the ISFOG pile driving prediction, we were still receiving very decent performance with those linearized models. So that was encouraging. You may have heard a lot about deep learning, because deep learning is very successful at image classification and recommending your latest Netflix suggestion for you to watch after this talk. And deep learning is actually a technique for which I try to reveal a little bit what is behind it. Because if you understand what is behind deep learning, you can also understand its strength and its drawbacks better. In deep learning, the features and the targets are connected through a series of hidden layers, with each hidden layer containing multiple neurons, multiple dots, as shown in this chart. And what happens at each of these neurons is that the values from the individual features are coming in. They are weighted with a given weight, and then the sum of the weighted values is taken and passed through a transfer function to calculate the output to pass on to the target or to the next neuron. The process of training an artificial neural network, which is what deep learning is all about, is a matter of optimizing these weights so as to, again, minimize the loss, the difference between predictions and observed value. There are no set rules to determine the model architecture, so depending on which hidden layers, how many neurons in the hidden layers you select, you can come up with different results, and that model architecture is often determined by trial and error. But even though it can be very powerful to predict problems with very large data sets, it can be relatively poor on problems with limited data. And in geotechnical engineering, for instance, for the pile driving problem, we only had about 3,000 data points, which was not a lot in terms of deep learning amount of data. The biggest downside, in my view, is that deep learning leads to black box models. So you don't really know what's going inside. There are equations that go between the different layers of the model, but it's very difficult to actually make any sense of them. So you need to rule out that your model is leading you to physically nonsensical behavior. So those are two regression models. There's other models which you can explore, but maybe more detail on that in the pre-conference workshop in Austin. But for classification, I also want to introduce a couple of example models. And the first is linear classifiers. So linear classifiers will subdivide the feature space. For this example, the logarithm of normalized cone resistance and the logarithm of normalized friction will separate that feature space using straight boundaries. This already says it itself. If you look at the Robertson chart doesn't really have straight boundaries. So if you have a problem that has in reality curved boundaries or a nonlinear relation making the distinction between the individual classes, those linear classifiers will not be very powerful. And you can see that here. For the Robertson chart, the cohesive behavior, the zone number 3, is more or less approximated using those straight boundaries. But in the zones where you have the curved boundaries, the sand and sandy silt regions, you have relatively poor distinction. I also want to show you again a confusion matrix, but now applied to multiple classes. And the confusion matrix immediately introduces that the predictions for the class number 3, the cohesive soil types, is quite successful. because in 91% of the cases, the model will predict that a point is clay, whereas the soil sample description also said that it was clay. For the sand and sand silt mixtures and silts, performance is much poorer, because if you predict that a soil, that a given sample is a sand mixture, so the class number 5, then it will only be that in only 57% of the cases. So the confusion matrix really brings out that difference and shows the strong points of this model rather well. Another model which is very common for classification is decision trees. And decision trees consist of a computer algorithm that makes a split in the dataset, so it creates nodes, and those splits are made to maximize the information in the dataset so that the partition contains data which is separated to give you the maximum amount of discernible information between the two classes predicted by the model. That splitting can continue for some time until the information gain is 0 or until you reach a maximum specified tree depth. And the advantage of this rule-based decision tree building is that you can capture nonlinearity on that basis. But the downside is, especially when the splitting continues for a very long time, that you will predict a class for each individual data point almost, and you will see overfitting in your data set, and the models will generalize poorly. This is visualized here for our CPT soil type data set, and you can see that if you limit the maximum depth of the tree to 4, so 4 layers of partitioning, then you will see that you are approximating the cohesive region, the sand region, the sand silt mixtures region, with those sort of blocky models, but they appear to be rather consistent, and there is at least some correspondence to the way the Robertson charts are drawn. But if you increase the maximum tree depth and allow that splitting to continue further, you see that you have these spurious regions appearing in the visualization. So in a very small difference between the logarithm of normalized cone resistance, you could jump from a clay to a sand and then a clay again. And that is obviously not the intention when we're building a model, to have these erratic behaviors, and things only get worse when we extend the tree depth. So at a maximum tree depth of 12, you can see that things are actually worse. Finally, for classification, we can use ensemble models. Ensemble models work by combining the predictions from several different prediction models, and those individual prediction models are called weak learners. The underlying thought is that the errors from the individual weak learners will cancel out relative to one another, and the aggregate prediction will be better than each individual prediction. Several ensemble model types exist, such as random forests. In random forests, you have several decision trees that are being trained on a random subset of the data, and then those decision trees are combined for final prediction. And another algorithm which is very popular these days is the XGBoost, or extreme gradient boosting algorithm, which tries to build a series of tree-based learners, with each tree in the series trying to minimize the errors from the previous step. That makes the technique quite powerful and a popular choice for data science competition these days. These ensemble models are generally successful, and that was also proven on our ISFOG competition, because the winning prediction was a CatBoost algorithm which does exactly that ensemble modeling. So finally, once we have our machine learning model, we're content with this, we are happy with its accuracy, and we also think that it generalizes well. It still pays off to interpret our model, because not all machine learning models, especially not the more complex ones which have no mathematical form, are directly interpretable. Linear models gives us an equation, but that's the exception rather than the rule in machine learning. In decision trees, you have a series of if-else statements, And in neural networks, you have the activations functions, the sums, etc. So it's very difficult to know exactly what's going on inside the model. So the question then is, how can we ensure that our model is still capable of capturing the underlying physics? Because as engineers, we're interested in models that represent the physics of the problem. And then we can do that in two ways. We can either feed the physical information to our model by using engineered features, such as cumulative shaft friction that takes into account friction fatigue during pile driving. Or if we already have a model, we can plot the dependence of the target, so the blow count, on variations to each input feature. And for instance, for the pile driving dataset, that revealed that there was a funny behavior in our model, whereas for low cumulative shaft frictions or low hammer energies and low depths, you would sort of get this jump up in blow count where you would expect it to go down to zero based on your physical knowledge of the problem, because if you have zero resistance, you should normally also need zero blows to penetrate the pile. So revealing that sort of non-physical behavior allows you to revisit the model and improve your machine learning. And machine learning really is an iterative process. So let me wrap up with a few closing thoughts. And I hope that after this talk, you may believe already that you are closer to machine learning than you thought you were, and you may be more excited to actually pick it up in earnest. Try it on an example dataset of yourself, or use one of the example datasets, such as the one from the ISFOG prediction event. Modern data science libraries or data science tools should allow you to get started very quickly. And when you build machine learning models, make sure that you also check their quality, check how well they generalize, and what their interpretability is. I think one of the main challenges, and that will not change, even though machine learning can enhance our profession, there still has to be a strong focus on high quality data collection, both in situ and in the laboratory. And if we can harvest that site investigation data, but also construction feedback and monitoring data to make sure that it doesn't get lost on project drives or within the knowledge repositories of individuals, then I think we can bring our profession further. So thanks very much for attending this webinar. It's been a pleasure, and I really hope to see everybody in Austin. It's very excited to now be in the final months before the conference is actually going to happen. Thank you.
Thank you very much, Bruno, for your presentation today. We'll have a few minutes for questions. If you haven't already, please type in your question through YouTube. We have a couple that have been sent to us already. I'll start with one. Generally speaking, Bruno, what amount of data do you really need to start building a machine learning model, right? I mean, can you just start with any kind of data or any amount of data, sorry?
I think it's possible. Of course, you will know from conventional engineering that fitting a straight line through 2 points is very easy and you have an exact answer. Fitting it to 3 points might be less satisfactory. If you gather more data, you will see what the shortcomings are in terms of your data set. I think it makes sense to start building models as soon as you would think that you could draw correlations between features. I think the data that we're typically using for geotechnical correlations is sometimes only in the tens or a couple of hundreds of data points. But building a geotechnical correlation is a form of machine learning. So why shouldn't we use machine learning on those limited data sets as well? But one of the things that you should gear your workflow towards is that your workflow doesn't really change when more data comes in. You can simply add to the data set, get more data points as you progress, and continuously improve the model coefficients or the model types as you go along.
Thank you. We have a question by Najan Hubaj asking, since data science will be part of our geotechnical practice, should we develop standards or guidelines for, quote, data checking, cleaning, end quote? How can we trust anyone's machine learning results presented to us?
I think transparency is really key in this, because if we're working on data and doing machine learning, we should be able to repeat the results that others have presented. I think any consultant that is doing machine learning for you should guide you in the process. But if you want to do a third-party check, that should always be possible. In that sense, there should never be anything hidden within machine learning. I think we need to communicate transparently. And in terms of data cleaning, it will always depend on the problems that we have. I think one of the main things that I would do is to really check outliers for physical representativeness. If it is really truly a measured value, then I think it's hard to discount it from the data set. If you see that the measurement system was malfunctioning, then there's a good case to remove it.
So in the same way as what we use today in industry in our practice is we use correlations that are published, and we adopt them because they work, but we also adopt them because they've gone through a peer review process many times. Do you think that peer review process would be some of the systems that we would be using for adopting machine learning processes of others?
I think so, and I think public data sets can help in that respect, because then the data is open to anybody checking it. Of course, there's a challenge there, because a lot of the data in our profession is proprietary, because it has it has a large value to the developers that are collecting this data. But we've seen in certain cases governments leading the way to make data sets public, and I think that can be used to good effect to advance, to really have that peer review and to work together as a community and perhaps proposing new correlations or defining a framework to continuously update them.
Another question from Andre Rudenets. How does the deep learning process incorporate real physical phenomena / soil mechanics during model learning?
Well, I mean, the philosophy behind deep learning is that if you feed enough data to it, it will eventually learn the physical behavior. But I've mentioned that data volume is is a big question. And if you don't feed the network with enough data, then the neural network might not have the capability to learn the physical behavior. And then you might end up with some funny behavior, like was shown in the slide on the model interpretability. So I like to always assess whether the deep learning model, whether it has actually learned the fundamental relationships between the data. And if that doesn't work, we can help it along by providing it with some physically engineered feature that already captures some of the known aspects of our problem. So instead of feeding it with QC, we feed it with cumulative shaft friction up to a certain depth to train itself on.
Thank you. Another question by Najan Hubaj. How variable were the predictions in the ISFOG 2020 competition?
Right. I don't have the numbers in front of me exactly, but I think in terms of our squared coefficients, we were around the 0.7 mark. So that is not great. It means that there's 70% of the variance in the data set that is being explained by our model. That is, of course, when we're looking at the accuracy of our model, and we can also approach it in a couple of different ways. I mean, for instance, for some problems, overprediction will be worse than underprediction. We could penalize overprediction more than we penalize underprediction. In other problems, it could be the other way around. I mean, imagine that you are driving the pile, then if you're overpredicting pile capacity, that will not be a good thing. If you're underpredicting it, you're on the conservative side. So in that sense, for the geotechnical profession, maybe those error metrics also need some thought and some discussion, because they may change for each individual project and each individual problem.
Thank you. I think we have time for one more question. And this one is from Hitesh Halai. I'm trying to understand this, but do you believe the problem of having high missing ratios of features due to the different sources and quality of data making up the overall data set?
I think I know what this question is getting at, because we don't have the measurements which we would like to have at each data point. For instance, grain size data is only going to be available at a couple of selected depths. It's not going to have the same kind of geospatial coverage as cone resistance does. And it's true that that limits us to a certain amount. I think they're aggregating multiple data sets and really looking across the boundaries of individual projects is going to help us along, because if we can collect those trends on larger data sets, then we could have sufficient data volume by aggregating the data, whereas the individual project clearly doesn't have that that data available.
Thank you, Bruno. We've answered the questions that most have put forward.
Thanks.
I want to thank you again for this incredible presentation on Data Science 101. And I invite everybody again to participate at the ISFOG 2020 conference. And I'll leave it to Brad to give our closing remarks.
Thanks, Rodolfo, and thanks, Bruno, for a great presentation, and for everybody for tuning in. And we had some great questions today. Fantastic interaction. We really appreciate that. Thanks, everybody, for being such a big part of this. And hopefully this makes all of you look forward to attending this in-person event even more later this year. I put it in the chat. Our next one is going to be on February 22nd in the afternoon, just like this. The presenter will be Philippe Jean-Jean from BP, also a member of our program committee. And the topic for that one is going to be new proposed ISO and API PY curves for piles. So you'll want to check that out. You can register at our Eventbrite page. We would love to see you there. So again, if you liked what you saw today, click that little thumbs up, give us a like, click subscribe, click get notifications. We will let you know every time we post something to the YouTube channel. Other than that, I don't have anything else. I will say farewell from the Charleston airport. The schedule for all of our upcoming workshops is up on the screen there. And certainly as those come up, you'll be able to register for those via our Eventbrite page as well. So thanks everybody for sticking with us today for the questions. Bruno and Rodolfo, thanks a lot. I think we had a good time, and we will see everybody next month.
All right. Looking